Hello, this is Britt Caswell with another example video. In today's video, I'm covering example 2 from section 7-5 in the SavvasRealize Algebra 2 textbook. The goal of today's video is to describe some key features of tangent functions. Just making a little more room for my triad, I think. There we go. Alright, so it kind of lists off the key features that we want to look at, so let's make sure that we touch on those, okay? Now, the first thing to talk about is the domain. Now, the domain looks really quirky for these. Okay, so what they tend to do is they tend to write this in set notation. Sorry, not set notation. Yeah, set notation. Because of the nature of the problems. An inequality won't show it properly, and intervals won't show it properly. So the thing is we look at all values of x where x does not equal pi over 2 or any increment of pi after that. Where x is a real number and n is an integer. So let's talk about what this means. So you can see that there's an asymptote occurring at pi over 2, 3 pi over 2, negative pi over 2. So this distance right here is the distance pi, right? Because 3 pi over 2 minus pi over 2 is 2 pi over 2, which would be pi. So every increment of pi after pi over 2 or before pi over 2 has another asymptote. So we have to describe that. So when we say x is not equal to those, this is describing an asymptote. And then here where we put the plus n times pi, that is telling us that it skips pi over and over and over, or over and over and over, okay? And they're very specifically saying that x has to be a real number, so no imaginary numbers, and n has to be an integer, like a counting number. Now it could be a positive counting number or a negative counting number, but it has to be whole, no decimals in there. Now the range of these works exactly as you would expect. Alright, so I could show that range with interval notation. That's easy. So our range, it goes down for forever, and the graph goes up for forever. So our range is all real numbers, or from negative infinity to infinity, or however you would want to say that. Alright, the next thing is the period. Okay, the period of this graph, remember how we were saying that it skips by pi units every single time? That is our period. Alright, there's not really much of a calculation to it other than the fact that you could see it bouncing between the asymptotes, right? Because it always hugs the asymptote on the left and hugs the asymptote on the right. Now think about the equation to get a tangent. Okay, so the tangent of an angle is equal to the sine divided by the cosine. And I mentioned this in our last video, but I'm going to re-mention it here. So anytime the sine equals 0, you're going to get a 0 on the graph. So you could see right here, those are where sine equals 0. And anytime you have the cosine of theta equaling 0, you're going to get an asymptote on the graph. Right? Because you can't divide by 0. So that's what's causing those asymptotes to happen, is that's where our cosine is equal to 0. Now when we go to talk about increasing versus decreasing, remember, you want to think about like a little kid on a skateboard who's going from the left-hand side of the graph to the right-hand side of the graph. Now, every single time he looks at this graph as he's going by, it's going uphill. So this graph is increasing everywhere. which is kind of weird for kids because they feel like the jump from before the asymptote to after the asymptote, they feel like that is decreasing. But remember, the graph doesn't exist on the asymptote. It isn't there. So it is always increasing because it doesn't exist where it goes down again, where it resets. All right. Now they also have this notation. I don't really want to write it down because I have messy handwriting. Let me go ahead and snip it from the book. And it talks about it being positive versus negative. And then of course it has these shaded graphs on theirs, but I didn't copy the shaded graph. But look at what it says. It says the function is positive for every interval. That's close enough. 0 plus n times pi. And they're saying pi plus 2 plus n times pi. So what they're saying there is that the function is positive. I could probably shade part of this. So the function is positive only in like this section. So it's in half of every single iteration of the graph. So we have to have that weird notation that we used for our domain to describe this little section. Alright, so this is how they're describing it. So 0 plus n times pi. And then they're saying at pi over 2 plus n times pi. And so this, I think, is describing like a range, right? So this is where the shading starts, and this is where that shading ends for each of these. And then they do that same thing to describe the negative. I don't have purple on my tool set, so I'm going to call it blue. But to describe this negative area, all right, here's the starting of each interval. And then here's the ending of each interval. So it's kind of weird notation. Not often used. This is actually the first textbook I've seen that has talked about this. So, is it a huge deal? Not really. Alrighty. So, let's talk about the cotangent. So, the cotangent is a lot like the tangent. It's just flipped backwards, right? So, in terms of our domain, actually, I'm just going to cut and paste from the book again and just describe it a little bit because I think it's easier to read than my handwriting. So the domain, again, the domain has to skip in patterns of pi. Okay. Now notice their n pi, they just have the n pi. They don't have the pi over 2. And that's because the cotangent is equal to the cosine divided by the sine. So wherever the sine is equal to 0, you're going to have an asymptote. Alright, so you could kind of see that on the graph here. Like the sine is 0 at 0, and at pi, and at negative pi. So you could definitely see that pretty easy, especially if I knew how to draw. But there's our asymptotes. And then you're going to have an intersection at 0 on the graph whenever the cosine is equal to 0. So when cosine of theta equals 0, you're going to have a 0 on graph. And so you could see that here. So the cosine is 0 at pi over 2, negative pi over 2, and then kind of continuing on. And so you could see it on the graph. That's where they're intersecting, right? Now the range, again, it goes from negative infinity to infinity because these graphs continue down for forever and up for forever. All right. Now the vertical asymptotes, it says x equals and then negative pi, 0 pi. I thought it was interesting that they didn't put this in interval notation. Or sorry, the set notation, not interval notation. Because it is a list that continues on for forever. Same thing with the zeros. I'd imagine you'd want some kind of notation that like matches the domain and range, but we don't really mention that often, so I'm not terribly worried about it. And then they describe the positive and negative values of the graph because you could see here it's positive in kind of a different set of intervals, right? So my greens are my positive ones. And so if you notice on the tangent, for example, it was positive from 0 to pi over 2. This one's still positive from 0 to pi over 2. And this one's positive from negative pi over 2 to negative pi. This one is still positive from negative pi over 2 to pi. So these are about the same thing. The only difference is that they changed the order of they called this n pi instead of 0 plus n pi, which I thought was interesting. All right, and in terms of negative, again, it follows that same pattern. So it has that same kind of wonky notation to it. And remember, this set of parentheses is describing an interval. So this first value is where it starts and then where it stops, right? Which is kind of weird for people, I think. And the last thing is that the function is decreasing from negative infinity to infinity. So they're saying all values of the function are decreasing. Now, I disagree with their notation on this because your like this is the same thing as saying like for all real numbers, right? But the graph doesn't exist at all real numbers. So like at pi or at 0 or at negative pi, the function doesn't exist there, so it can't be decreasing there. So I don't agree with that notation, but there it is. So that's some of our key features of tangent functions. Until next time.